So now we have an origin and we have the xyz coordinate, which is not moving and it's fixed in the space. It's a position and orientation fix. And this is an arbitrary 3D curve. The particle is moving on it, and the position vector of the particle r is now projected onto the x-axis, y-axis, and z-axis in a perpendicular manner. So we get x, y, and z coordinates for this vector r. So we write vector r as x times I plus y times j plus z times k, where x, y, and z are the components of the position, and I, j, k are the unit vectors of x, y, z axis. So we know this one for sure. Now, the distance of the particle from origin is clearly the magnitude of r, which is a square root x squared plus y squared and plus z squared. Now, the important parts are calculating velocity and acceleration. So to calculate velocity, what we need is to calculate the time derivative of position vector r, right? So we have, in the Cartesian coordinate, we have r to be x times I plus y times j plus z times k. By the way, whenever I use this hat means that quantity is a unit vector. So if I use arrow means it is a vector. If there is a hat above it, it means it's a unit vector. Magnitude of it is 1. So now I take a time derivative out of this. And we know time derivative of r is what? Yes, velocity. So velocity is going to be dx over dt times I. Now we know I, j, and k are constants. Their magnitude is 1, their direction is fixed, therefore they do not have derivatives. If they do, then this is a product, and we have to apply the product derivative. So it's going to be derivative of x times I plus x times derivative of I. But I, j, and k do not have time derivatives because they do not change. So it's going to be just dx over dt times I plus dy over dt times j plus dz over dt times k. Okay, so that's the formula for velocity. Now, we use a notation from this point on in the textbook, and that is the notation dot. So whenever we take the derivative of any parameter with respect to time only, we show that derivative by dot. So instead of dx over dt, we use x dot. So dot means time derivative. Or this one is going to be y dot, and this one is going to be z dot. Okay? So dot is basically what? Time derivative. Then you might say, what is prime? So what's the difference between, let's say, y prime and y dot? Well, y dot means derivative of y with respect to time. So what about y prime? Then that's the derivative of y with respect to something else. For example, if y is a function of x, right? Like you have a 2D curve, and this is x and this is y, and this is the function of y. So y prime means derivative with respect to, for example, here x. Or if it's a function of z, derivative of z. Okay, so we reserve dot for time derivative and prime for other derivatives, derivative with respect to other variables. Okay, so we're going to keep this notation throughout this course, and probably you'll see that later in your courses. So just wanted to clarify the dot operator. So now our formula for velocity becomes v is equal to x dot I plus y dot j plus z dot k, and let me use the regular x instead of this. Okay, so that's the velocity vector as described in Cartesian coordinates. Now, if somebody says, what is the magnitude of velocity, or in other words, speed? What is the magnitude of the velocity of the particle? Of course, it has these three components, x dot, y dot, z dot. So the magnitude of it is going to be calculated by the square root formula, right? So this is the magnitude of velocity. The other thing important is the direction of velocity, right? We learned in the past that velocity is always what? Tangent to the path. So if I want to know in which direction, along which direction the particle is moving at the moment, is going to be the direction of this velocity, right? So speed is the magnitude of it, but the direction of motion is the direction of this vector v. And if you remember, the direction of any vector is shown by its unit vector, u sub v. And how do we calculate unit vector? Yes, unit vector is the vector itself divided by its magnitude, right? So this guy is the speed, the magnitude of the velocity, but the direction of motion is shown by vector uv, and I'm going to use hat again because it's a unit vector, which is calculated by vector v itself divided by its magnitude. So we have to divide this vector v by this magnitude. So you're going to get x dot over this square root times I plus y dot over this square root j plus z dot over this square root times k. See if it allows me to copy. No, apparently it does not. Okay, so if it doesn't, that is fine. I write it. I'm still not a pro using this software. So this would tell you what? The direction of motion. So again, magnitude v shows the speed, direction of v, unit vector v shows the direction of motion, which is also what? Tangent to the path, okay? So if you want to find the direction of tangent to the path at any point, just use u of v. That is very, very important. And finally, acceleration. Of course, we take another time derivative from velocity. And since the components of velocity were x dot, y dot, z dot, now the components of acceleration are what? X double dot, y double dot, and z double dot, right? So if I write them for you here, A is going to be x double dot. Double dot means two time derivatives, right? Plus y double dot j plus z double dot k. Again, double dot means time derivative twice. And now magnitude of acceleration is going to be using the square root formula. Okay, and then the unit vector of acceleration is going to be something similar to magnitude of velocity. Now you might ask, what's the importance of this magnitude and direction of the acceleration vector? Because the magnitude and direction of velocity vector, they give us how fast the object is moving and in which direction it is moving. What about this? These two quantities, what do they give us physically? What's the meaning of them? Right? What do you think? So for them, we have to know the second law of Newton. Second law of Newton says what? It says sum of the forces is equal m times a, right? So if I know vector a, since m is a positive constant, what happens? The direction of f is the same as direction of a, right? And the magnitude of a is magnitude of f divided by m. So what does this give me? This is also equal to sum of the forces, the magnitude of it divided by m. So it is an indicator of total forces, the magnitude of the resultant force that is applied on the object scaled down by the mass of the particle. Okay, so it shows how much force is applied on the object. The bigger magnitude of a is, the more force, the bigger the resultant force is. And magnitude of a, it's showing also direction of a shows what? The direction of f. Okay, so this is the same as the unit vector for f. So it shows in which direction the resultant force is. So shows, let me write it for you, the direction of the resultant force. This one is proportional to the magnitude of the resultant force. So it's not equal to that, it's proportional to that, and the reason is we are dividing it by m. Okay, so these are also important. Okay, so now that we learn all of it for rectangular coordinates based on these dots, now let's look at the specific cases, and the specific case that we're going to look at is a projectile motion. So projectile motion is if under some assumptions can be basically easily calculated, we can provide very nice looking formulas like these on this page. If we assume some conditions in the beginning and during the flight of the particle, the projectile, we can end up with very simple formulas. If not, those conditions are not valid, then the equations will be quite ugly and nonlinear. So let's first look at the projectile motion. So in projectile motion, we assume that a projectile is launched from an arbitrary position x0 and y0, an initial launch position. The launch velocity is v0, which has an angle measured counterclockwise positive with respect to x-axis of theta. So theta is called launch angle, v0 is called launch velocity, x0 and y0 show the launch position. And if we allow this projectile to move, and if there is no crosswind or nothing, then we can assume that this motion will stay on the same plane during the entire flight of the object. And in this case, we assume that plane is xy plane. Now, to make life easier in deriving the equations, we assume the very important thing that the effect of the air on the particle is neglected. In other words, drag and lift, the effect of the air on the particle they are both considered to be zero. We know in real world it might not be the case. It's actually never the case unless you shoot something in the vacuum. But now how much are the effect of those, we'll probably see later on. But again, if we include the force of the air, drag and lift, you will never ever get formulas clean and nice like this. So what should we do? That's the trade-off of engineering. Do you want to go for more accurate and include drag and lift, and then end up with a bunch of differential equations, nonlinear, that you cannot solve and you cannot get formulas like this? Or you want to do some assumptions, simplifications, like forget about air and get these nice formulas. So it depends on the application, okay? It does depend on the application. In real life, we mostly should not just neglect it, okay? So one example is, let's say you are the designer, the engineer for a stunt person, right? And this stunt person is just going off this ramp, and then he wants to fly some big gap and then land on the other side, right? So if you are the designing engineer of that, you do not want to neglect anything, right? So by no means you want to neglect anything, because if this gap is so many feet or so many meters, and then you have some velocity here, and then some angle which comes from the platform for jumping, if you neglect the effect of the air and say, well, all you need, all velocity, because that's the most important thing, how much speed does this guy need to successfully jump the gap? And if you neglect the drag, then the estimated value that you have for V is going to be less than what he really needs. So he end up here, and he's going to kill himself, okay? So drag definitely does matter. And actually in some applications that I'm going to show you later, or maybe I can show you right now, in many applications, the effect of the air is so significant that it can determine the motion of the object. So let me show you. One of them is called the Magnus force. Basketball. Take a look at this. This is very interesting. Okay, so here is the guy who is throwing a basketball down a very tall dam. Okay, and look, first he releases the ball, okay, from a very high altitude, and he's not going to give it any spin. And it goes down kind of as predicted and hits the body of the dam. Okay, so no huge change in the trajectory. This deviation that you see is because of the shape of the dam and the way that it is being videotaped. But now look, he's repeating it, but this time he's giving it a spin and let it go. See what happens. Look. Did you see the huge difference? Instead of going straight down, now it is completely curving and going somewhere else. It goes to the body of the water. Look. Completely goes to a different thing. So it significantly changes the trajectory of the particle. Just giving it a little bit of spin, because spin creates a huge amount of force, lift force, which in this case we call it the Magnus force. So you see, it's the difference between this one and this one. So not always you can easily just neglect the effect of the air. So here we assume very simple cases, short travels. Okay, this is much more significant when it is a line trajectory. If you are throwing a basketball inside the basket and it's just a few feet away from you, it's not going to be significant effect. While when this gap is too big, and especially if the object can have a spin in the beginning. Now the motorcycle is not going to have a spin, but the basketball, you can give it a spin. That's going to make a huge effect. The other one is from this Magnus force. Okay, so what I showed for you, and you can search it for yourself, is what many soccer players are using when they want to kick a ball. They give it an initial what? An initial spin. So they don't directly just kick it, they give it a spin while they're kicking it, and that's where you see the ball gets this crazy curves. Okay, that's also because of the Magnus force. So just wanted to remind you of the importance of air drag. But in this case, to derive those nice looking equations, we neglect it. So what happens when the particle is in the air? The only force acting on it is what? Gravity, okay, in the downward direction, opposite to y. And so that's where we start getting our equations, okay? So let's take a look. So in this case, in projectile motion, equations without the air effects. Okay, so the most important thing is no air. So when this particle, as I said, is in the air, and this is my coordinate system, the only force acting on the object, if I draw the free body diagram, is mg in the y direction. And although we are not going to use Newton equations in this chapter, is for next chapter, but if you just look in the x direction, there is no force on the particle, so it's equal to mass of the object times acceleration in the x direction, and this is 0, therefore there is no acceleration in the x direction, right? Ax is the same as what? X double dot, right? Ax is the x component of acceleration, and we know from our previous notations that the x component of acceleration is called what? X double dot. The y component is y double dot, the z component az, right? The same here, right? This one is vx, this one is vy, and this one is vz. Okay, so there is no x acceleration. Now in the y direction, on the other hand, the sum of the forces, which is equal to mass times acceleration in the y direction, this is equal to negative mg. Negative because this is opposite to the direction of y. And if you simplify m's, then you see that the acceleration in the y direction, it is equal to negative g, okay? So we start by these two equations, and we integrate these two equations in the boxes twice to get velocities in the x and y, and to get position of x and y. So if I call this guy equation number 1, now I'm going to integrate it one time. What would happen is, if you remember, first of all, you see both of these accelerations, x dot and x double dot and y double dot, are what? Constant. And whenever accelerations are constant, if you remember from our previous lectures, we have these nice formulas, right? The ones in red. This one, and this one. These are valid when the acceleration a is constant, so I can use them. So this is, I write it one time for x, one time for y, all three of them. One time I can write them for x, one time I can write them for y. So first let's write this velocity versus time equation for the x direction. If I write it, what do I get? It's gonna be Vx at any time point is Vx at time 0 plus Ax times t, right? So again, I'm writing this velocity time equation in the x direction. Now, Ax clearly is what? 0. And Vx at the beginning is what? Well, if you look at here, in the beginning, the velocity is V naught at angle theta, right? So if I decompose V naught along x and y, in the x direction, V naught of x, and in the y direction, V naught of y, what is V naught of x here based on V naught and theta? Yes, from your trigs, you know V naught of x is V naught cosine theta, and V naught y is what? V naught sine theta. So this guy is V naught cosine theta. So now I got my first equation, that Vx at any point is equal to V naught cosine theta, and it is not going to change. Why? Because there is no x acceleration. Okay, so Vx will never change. In other words, in the x direction, what type of motion do I have? Yes, it is constant acceleration, but that constant acceleration is 0. What was the name of the motion with 0 acceleration? Yes, you're right. It is called uniform motion. So in the x direction, my motion is called uniform motion, because the acceleration is 0. Okay, so that's the equation for V, and then if we integrate it one more time, or we go back to the uniform motion equation, in the uniform motion there is only one equation for position. Position is initial position plus constant velocity times t. So if I write it, my x position is always my initial x position plus what? My constant velocity times t. So this is how my x is going to change versus time. It's the initial position plus a constant number times t. So it's a linear function of time. X is changing linearly with time. So these three, the red one and the two green, are x equations. And then we come to the y equation. Now a of y is constant. Therefore, if I write my v of y equation, v of y is v of y initial plus a of y times t, the same format, right? But this time a of y is not 0, it's negative g, and v naught of y, if you remember from the diagram, it is v naught times sine of theta. So if I write it, you're going to get Vy is equal to V naught sine theta minus G times T. Okay, so you see V of Y does change with time, but linearly, because in the Y direction, what type of motion it is? It is constant acceleration motion. So it's kind of an interesting motion, right? In one direction, it is uniform motion. In the other direction, it is constant acceleration. So it is both of these types of motion at the same time, which is very interesting. And then if I integrate this one more time to get the y position is initial y plus initial vy times t plus half ay times t squared. So if I integrate this one more time, I'm going to get y to be y naught plus initial vy, which is v naught sine theta, times t plus 1/2 of acceleration. Acceleration is g, so it's going to be negative 1/2 g times what? T squared. And this equation is the y equation. So you see y does change with time in a quadratic manner. Okay, so these are the equations for Vx, Vy, x, and y, which you of course can see in the lecture. I just derived them for you so that I can relate them to the previous lecture. So these two equations and then these two equations, right? 1, 2, 3, 4, I derived for you. Now I can easily show you also if I write my time-independent equation, which is this guy. If I write it for the x direction, since a of x is 0, it gives me that v of x squared is always v naught of x squared, but v of y squared is v naught y squared plus 2 times negative gy minus y naught, which is actually this equation. This one. So this fifth equation is the time-independent equation in the y direction. Okay? So in the time-independent equation for y direction, I have v squared y is equal to v naught squared y minus 2g times delta y, which is y minus y naught. In the x direction, I only have vx squared is equal to vx naught squared. But since the ax term is 0, the rest of it will be 0. So these two are time-independent equations. Of course, the bottom one says vx is equal to v naught of x, which is what I have over here in the green box. So it's nothing new. But now if I add these two guys together, what happens? This is going to be vx squared plus vy squared on the left side. But what is vx squared plus vy squared? Yes, based on what we had, the magnitude of velocity, look at this. Look at this formula. The magnitude of v squared is going to be x dot squared plus what? Y dot squared, but x dot is called vx and y dot is called vy. So when I square them and take the square of both sides, what do you get? Yes, this left-hand side is going to be magnitude of v squared. This is going to be magnitude of v at the beginning squared, and then that one will stay. So you can get this equation, which is very similar to this one, except these two quantities, v and v naught, they don't have subscript y. They are general initial v and total v at any point. Okay, which is this bottom one. So you can use either one, okay, depending on how you would use that. Now, one of the most important equations, which I'm not sure if you have seen or not in your physics, because probably most of these you have seen in your physics. The one that is really important is the equation of time-independent equation, which is between x and y, no velocity is involved. So in order to get that equation, what I need is, if I call this green equation equation 1 and I call this black equation equation 2, what I need is to eliminate t between 1 and 2. So from 1, I would find my t, so t clearly here is going to be x minus x naught. So first I take x naught to the left and then divide by what? By v naught cosine theta. And x minus x naught, I call it what? Delta x, if you don't mind, right? That's the definition of delta x. So I use this and I call it equation 3. And then I plug 3 into 2, I'm sorry. And eliminate t. By the way, I take this y naught to this side, and y minus y naught, I call it what? Delta y. And then now, if I plug in, this v naught sine theta is multiplied by this t. So that v naught in numerator and denominator would cancel. You're going to get sine over cosine, which is tangent, and delta x and tangent of theta. So you're going to get delta x times tangent theta, right? And the t is eliminated because you replaced it. And then minus g over 2, and then t squared is going to be delta x squared over v naught squared cosine squared of theta. So you're going to get this very, very important equation where there is no time. It's only between y and x. And if you look at this, if you plot this guy in the xy plane, you want to know what kind of shape is a trajectory. So if in the simple case that we assume that x naught and y naught are equal to 0, it's going to be simpler to visualize because now delta y is the same as y and delta x is the same as x. So it's going to be y equal, we know when the projectile starts, theta is constant. Theta is the launch angle, and v naught is the launch velocity. So v naught and theta are what? They're not going to change, right? They are initially determined. They are constant numbers now. So it's going to be a constant number times x minus another constant number times x squared. So it looks kind of like this. Y equals a times x minus b times x squared. It looks like this. And what kind of curve is that? Yes, you are right. It is a what? It is a parabola. If x and y naught are not 0, then still a parabola, but not starting from origin. Okay, so what shape would you get for a trajectory? Parabola. It's a parabola. And again, all of these formulas, everything, this parabola shape, everything that we got is assuming one important condition. And what was that? This one. No air effect. If air effect comes in, so you have drag and lift, then there will be extra terms here to some of the forces, and then your accelerations are not going to be even constant, not in x, not in y, and they are impossible to integrate easily versus time. So you're going to get highly nonlinear second order ODEs, and it is not going to be so easy, as I said, to integrate. But physically, what would it give you? So let me give you a physical sense of it, at least. Later, we might be able to do that simulation in MATLAB, numerically solve those differential equations, and I'll show you the effect of those. But just roughly, if I want to show you a sense of what would be the effect of drag or lift, especially drag, because lift shows itself when you have a spin. Not always your trajectory has initial spin. But so here is a trajectory shot at origin. Okay, and let me do it again. Okay, so we shot this with the initial tangent velocity v naught and with the angle theta. If I shot it from the origin, this is going to be completely symmetric. Okay, so if I find my max height point here, the left side of this curve and the right side of this curve are completely symmetric with respect to a vertical axis passing through the max height point. It's perfectly symmetric if there is what? No drag. So the red curve is going to be no drag. Now, if I do the very same thing, the same launch position, launch velocity, and launch angle, but this time I do include drag, then you won't get something like this. That first of all, it is not going to be symmetric anymore. You cannot find any point with respect to which the left and right side are symmetric. It's not going to be symmetric. And this distance, which is the horizontal distance of the point at which the projectile hits the ground, measured from the origin, this here, which we call what? We call it range, okay? This range is definitely going to be shorter than the range where there is no drag, because drag is like friction. It does take the energy of the projectile, initial energy, and will not allow it to go its full range. Okay, so non-symmetric smaller range is gonna be what happens with drag, and it physically makes sense. And I'll show you later in simulations. Now that I talked about range, let me give you another formula which is about range, and then maybe another or a couple of other formulas about the max height point, so that we can work on this projectile motion in our lecture today. And then I'm going to solve this problem 1375. Then, to go more in depth of XY motion or rectangular motion, in the classroom, we're going to go through problem 1390, which is a start problem, so it is more difficult than a regular problem. And for this, we have to do a ton of chain rule and implicit derivatives. So we're going to do this in class, but I want to first give you a couple of more formulas on the top of lecture, and we solve this problem together, and then we continue. So first thing is, what is range? Okay, so if you remember our equations, x was x naught, or if I go back to the time independent equation, the time independent between x and y was delta y is delta x tangent of theta minus g over 2 delta x squared divided by v naught squared cosine theta squared, right? So this is the equation between x and y. Now, what happened at range? So at range, clearly you see that the height of the impact point and the height of the launch point are going to be the same. Okay? In a simple scenario like this where you start from origin. So what is delta y? Delta y is y minus y naught, which in this case, since I go back to the same elevation, it should be equal to 0. And delta x is current x minus initial x. So this range is going to be the same as what? Delta x, right? So if I go back here, when the projectile hits the ground, delta y is equal to 0 and delta x is equal to what? Range. I show it with parameter r. Right? So I get r tangent theta, or r sine theta over cosine theta, minus gr squared over 2 v naught squared cosine squared theta is equal to what? 0, right? Which is a quadratic equation in terms of r. And if I solve r or factor out r, clearly one answer is r equals 0, which is not the case. So if I simplify one r and solve for the other r, what would you get? You're going to get 2 v naught squared sine theta cosine theta. One cosine can also be simplified. Then divided by what? Divided by g. Right? And if you know tricks, 2 times sine theta times cosine theta is what? It's sine 2 theta. So there's going to be v squared, v naught squared, sine of twice the launch angle divided by g. So this is a simple formula for range. V naught squared sine of 2 theta divided by g. Now, it shows you something. Since V naught is constant, so if, let's say, you want to shoot something, and your power is the same, so you have no control over power because you are using, let's say, the same ammunition. All you can change is the launch angle, theta. And you want to know at what angle you're going to get the max range. Clearly, since g is constant and you cannot change v, the only thing you can change is theta. And so the max that you can get out of a sine function is what? 1. And when does that happen? When the angle of the sine is what? 90 degrees, right? 90 degrees gives you sine equal 1. So 2 theta is 1. Therefore, for what theta, you're going to get the max range. That's right, 45 degrees. So maximum range can happen at 45-degree launch angle if you cannot change the knot. Okay, so that is a formula for range. Also, the other thing is the max height. Okay, when is it, or if somebody says I line something with theta and v naught, what is the max height? This one here. What is this delta max, delta y max, which I can show with parameter h? How long does it take for the projectile to reach there, and how high it can go? Okay, which formula do we use? What's specific about this point? What do you think? What's specific at the apex point? The object does never go above that. Why don't you go above that? Because your v of y is equal to 0. If you remember, let me draw it again here. If you remember, velocity, the total velocity v at any point is always what? Tangent to the projectile. Right? So this is the initial velocity v naught at the beginning, but at the top, since it's max point, the total velocity v is what? This is also equal to the total velocity in the beginning. The total velocity v is horizontal, right? At any arbitrary point, you have some angle alpha, and your v has two components, a vx and a vy, right? Where vx is cosine alpha times v, vy is sine alpha times v. But at the top, the vy component is 0, otherwise this guy keeps going up further. But since I'm not going up anymore, all I have is vx at this point. There is no vy. That's this figure that I have also in the lecture, which is a very nice figure. If you look at this figure, so at the beginning, you have both of the components, x component and y component, because your theta is not 0, or it's not 90 degrees. As you move up further and further, what happens? Your x component never changes, right? Because we learned that my x component does not change my v of x. It is always equal to v naught cosine theta. It does not change with time. So the blue component, the horizontal component, never changes. But what happened to vy? Look at this formula. Initially, it's equal to v naught sine theta, a positive number. But as time goes, this negative term, negative gt, will make vy first get smaller and smaller until it goes to 0. So you see here, it gets smaller and smaller, and here it gets what? 0 at the top, and then after it goes 0, now it goes what? Negative. And negative means now I'm going down. And it gets a bigger negative number, bigger magnitude, I mean. So it gets bigger and bigger in magnitude until it hits the ground. Okay? So that's what happened to the projectile. Now, so at this top point, v of y should be equal to what? 0, right? So v of y, which is equal to v naught sine theta minus gt, should be equal to 0. If that happens, you can find the time it takes for it to go to the top. And it is clearly going to be v naught sine theta over g. This is the time it takes for a projectile to reach the highest point. And now if I plug this back into my y equation, which is this guy, if I plug that t back into my y equation, I see that h, which is equal to delta y, it is going to be v naught sine theta times g. So this is going to be v naught squared sine squared of theta divided by g minus g over 2, right? Let's make sure we are not making any mistake, because we have to multiply that t I found by v naught sine theta. So it's v naught squared sine squared divided by g, that's correct, minus g over 2t squared. So this is going to be t squared. Okay, and now this g and this g would cancel. These two quantities are the same. It's just one of that, it's 1/2 of that. So what would you get? 1/2. So h is going to be v naught squared sine squared theta over what? 2 times g. This is the max height that you would get. Okay? So this is the max height h. This formula is the range. And this is the time that you go to the max point. What is the flight time? Flight time is the time from the when you launch it all the way to it hits the ground. If you remember, I told you this parabola is perfectly symmetric. So if it takes me t seconds to come from here to here, it takes me the same exact t seconds to go from max point to the ground again. So the flight time is 2 times this t. So t of flight, the total flight time, is going to be 2 times t, and it is going to be 2 v naught sine theta divided by g. So how long will the projectile be in the air? This much. How high would it go? This much. What is going to be the range? This much. All based on one single assumption here. The assumption we did was what? That x naught is equal to y naught equal to 0. If that's different, then you're going to get a little bit different formulas for these guys. Okay, so these 3 formulas, t flight, range, and height that I gave you, max height, they're all based on this important assumption that we started from the ground. If you start off the ground, then you're not going to get the exact same formulas. So whenever we use any formulas in this course, we need to make sure we know the underlying assumptions. If they are not valid, we cannot use those formulas. One example is this problem that we're going to solve right now. So problem 1375 says a pilot wants to drop some survey marker somewhere in Australia. He's flying at 40 meters per second and completely horizontal. Then he would release the box completely without any initial velocity. So at what distance from right below the airplane would that marker hit the ground? First of all, why doesn't it directly go down? Why does it go and land in front of the airplane? Why? Because this parcel here is moving with the airplane. And although you release it, it does not have 0 velocity, so it's not going to be a free fall. It does have the same velocity as the airplane because it is moving with the airplane. So the launch velocity is v naught, but the launch angle theta is what? What is the initial angle? 0, right? Because it's horizontal. And we want to know how far in front of the airplane it would land if the airplane is flying at an altitude h. Okay, so if we look at this problem together, so this is our airplane, and this is the ground. The first thing we need is to set up the coordinate system. Where do you want to put it? And where is the origin? So the location of the origin does not matter. You can put it anywhere you want as long as it is fixed. So you can put it right where the airplane is. You can put it right on the ground, right below the initial position of the airplane. You can even put it at the end. Regardless of where you put it, the answer is the same. So for simplicity, I assume the origin is right below the airplane when it is gonna release the parcel, or the marker in this case. So I put my coordinate system here. This initial height is h. It is moving with, this is our box or marker or whatever. It is released with the launch velocity, or the speed of the airplane, which is 40 meters per second. And clearly the launch angle here is 0 degrees, right? Because I'm releasing it horizontally. And as we know, it is going to go through a parabola and hit the ground here, and I want to find this distance d. So this h is a given parameter. So your d will be found in terms of h and 40. So this is my projectile problem. And there are a ton of formulas that I have here. Not a ton, really, but 6-7 formulas here. And you might wonder, okay, which one should I use? So first of all, the problem is asking about the horizontal displacement, d, right? This d is the same as what? It's delta x, correct? Final x minus initial x. And this h is related to delta y. So delta y is given, v naught theta is given, delta x is to be found. Now the question I have for you is, anywhere in this problem, does the problem ask for time? No. Nobody here cares about time. All we care is x. So first of all, we need an equation in which there is x and hopefully no time. This equation has x, but it has time. Then I don't have anything until I come here. This equation has x and y and v naught and theta, but no time. So this one is a perfect equation. So I'm going to use it. Delta y is delta x times tangent theta minus g over 2. And then delta x squared divided by v naught squared cosine squared of theta. Now, delta x in this case is equal to d. What is delta y? Because delta x means what? X minus x naught. And delta y is always y minus y naught. Let's calculate these two guys. What is delta x? It's final x, which is d units away from the origin, minus initial x. You release it from the y-axis, or initial x is what? 0. So you see your delta x is equal to d. What about delta y? What is your final y? Final y is here, where it hits the ground. It is clearly what? 0. But what is your initial y? It's h. So your delta y is what? Equal to negative h, not h. And theta is 0. And we know tangent of 0 is what? 0 and cosine squared of 0 is what? 1. And delta x is d, and this is d, and this is negative h, and v naught is 4d. So if I solve here for d, this term would go away, right? And if I cancel the negatives, multiply by 2, divide by g, and then take a square root to get d, d is going to be what? And the v naught can come out. It is going to be 4d square root of 2h over g. And this 4d, remember, that was v naught. So this is going to be the distance. Does that make sense? Yes. The faster I move, the further away it lands, and the higher I fly, the further away it lands, right? But they are not both the same effect. V has a linear effect, h is just under a square root, gonna affect d. Okay? So if you want to land in half of the distance, you have to either reduce your speed to half of 4d, or you have to make sure that the square root h goes down by a factor of 2. So you have to bring your flying altitude by a factor of 4. Okay, which one is safer? Probably reducing the speed. Right? You don't want to go, if you are flying at 400 feet, you don't want to go at 100 feet, right? Especially if you are doing a drone delivery, right? You don't want to go too low. So that is completely making sense. Now, as I said, this problem 1390, we leave it for the classroom. And hopefully we can solve more problems. Okay, I'm going to mark it later. The other part of this lecture that is remaining is angular motion. So when a particle is going along a path, especially along the circle, we can measure, or we can define and then measure an angular position, not for the particle, but for the line that connects the particle to the origin, which we call the position vector. So for the position vector of the particle, we can define an angular position. Because we learned that when we are talking about particle, the orientation of the particle itself does not matter. But the orientation of the position vector might matter. And when does that matter? We're going to see later when we go to cylindrical coordinate. This parameter theta is one of the 3 coordinates. So we need to take a look at that ahead of time so that later when we want to drive our equations for kinematics, we don't have too much of a problem. So what we do is, if this particle is moving here on a circular path, at any point I define the angle for the position vector OB measured in a counterclockwise manner from the positive x-axis. So it is positive if it's counterclockwise. If it's clockwise, it is negative. So theta is called the angular position, and then if it changes versus time as the particle moves, the change in theta I call angular displacement, and I show it by delta theta, and the unit for measuring theta and delta theta is radian. Okay? Then we define, similar to what we did in the past, when we had r and delta r, then from change in position we define what? Linear velocity v. Here that the angle changes, the rate of change of angle versus time, I call it what? Angular velocity, omega. Okay? So omega is going to be rate of change of theta, d theta over dt, or delta theta over delta t, as delta t goes to 0. So omega is called angular velocity, and there are different units for that. The standard unit for it is, of course, the standard unit of angle versus time, so it's radian per second. Many times you hear another unit for omega, which is called RPM, or revolutions per minute, which can easily be converted to radians per second. If I multiply radian over second by 2 pi over 60, I'm gonna get revolutions per minute. Why? Because one revolution is 2 pi radians, and 1 minute is what? 60 seconds. Okay, so again, angular velocity omega is defined as d theta over dt. This is instantaneous angular velocity. We can similarly define average angular velocity, which is delta theta over delta t. Similar to v and v bar, now we can define what? Omega and omega bar. Okay, so this is the limit of omega bar as delta t goes to 0. And as I said, the one unit for that is called 1 RPM, which is 1 revolution per 1 minute. But 1 revolution is 2 pi radians, right? 360 degrees. And 1 minute is what? 60 seconds. So you see, if I want to convert the standard unit, radian per second, to the unit that is used a lot here and there, RPM, all I need is to multiply radian over second by what? By 2 pi over 60. Okay. Similarly, I can define rate of change of omega and call it angular acceleration alpha. So alpha is d omega over dt, or second time derivative of theta. And I can also define an average angular acceleration. So alpha, instantaneous angular acceleration, is d omega over dt. It is also the second time derivative of theta with respect to time, just like we defined A was second time derivative of position with respect to time. Okay, so this is instantaneous angular acceleration. And I can also write this d omega over dt by chain rule. I can write it d omega over d theta times d theta over dt. Okay, again, I'm using what here? Chain rule. It's like, again, these two d thetas are cancelled. And then what do I get? The omega over dt stays, but the theta over dt is omega. So I'm gonna get alpha equals omega d omega over d theta. And what do I call this? I call it time-independent equation because there is no time. Or I can, if you want, I can cross-multiply and get alpha d theta is equal to omega d omega, and then I can what? Integrate it. This is from theta 1 to theta 2. This is from omega 1 to omega 2. And so this is going to be omega 2 squared over 2 minus omega 1 squared over 2. And therefore I can call this guy, or the equivalent differential form of it, I can call it what? Time independent equation for angular motion. Okay. I can also define an average angular acceleration alpha bar, which is delta omega over delta t. The unit for angular acceleration is, of course, what? Radians per second squared. Okay, so now I have angular position, angular velocity, and angular acceleration. The same way that I defined linear position, linear velocity, and what? Linear acceleration. So the formulas that I could derive for constant velocity or uniform motion and constant acceleration motion, these formulas in red and this one, I can rewrite them the same way, but I replace linear position s with angular position theta. I can replace linear velocity v with angular velocity omega, and I can replace linear acceleration a with angular acceleration alpha. If I replace those, then I can get similar equations that I had here in red for linear motion. I can get them all for what? For angular motion, right? So if I create a table here, and this side I call it linear motion, and the right side I call it angular motion. The equivalency is this. If I have s position, right, in a rectilinear motion, here I have theta. If I define v here, here I have what? Omega, and I had a, here I have what? Alpha. Then whatever formulas I had here, I can replace. For example, so I can say these are the parameters or quantities, right? Then in uniform motion, what equations did I have? If you remember, I only had one equation really, which was position was equal to initial position plus the constant velocity times t, right? Here I can get the same thing. Angular position is initial angular position plus constant angular velocity times t, right? So this formula here, now I can apply it to angular motion, and look, that's this formula. Uniform angular motion, that's where omega is constant. Where in real life you see a constant omega? Probably in your clocks, right? As long as the battery is good. It's a constant omega. So the change in angular position of the handles can be linearly proportional to omega versus time. Then if I have constant acceleration motion, if you remember, I had three formulas back there, right? In red. So I had V was equal to V naught plus AC times T. So here A was constant. Then I had S was equal to S naught plus V naught times T plus 1/2 acceleration times T squared. And then I had V squared at any point is V naught squared at any point plus 2AC times delta S, right? Here I can write the very same thing. I can say omega is equal to omega naught plus alpha c times t, assuming alpha c is constant. And I can say theta is equal to theta naught plus omega naught times t plus half of alpha c times t squared. And then omega squared is omega naught squared plus 2 alpha c times delta theta. So you see, it's just plug and play. It's just replacement of parameters. Then I can have these formulas side by side. Okay, which you can see these three formulas here. Now, there are two things we have to discuss. One is a bonus question, which we'll talk about it in class. I want to clarify it in classroom. And then we have one problem 1393. So I leave this bonus for the classroom, and then this problem 1393, we'll do it right now. So it says, the airplane has opened up, has deployed the landing gear, and it is stationary when you land it, when you open it up, when you deploy it. But as it touches the runway, when it's trying to land, it gets this huge alpha of 110 radians per second squared. I want to know 1 second after the contact started and the alpha is staying the same, how much is omega and how much rotation has happened. Okay? So this problem says, initially at the beginning of t, when t is 0, it's stationary. So omega naught is 0 radian per second. Alpha is 110 radian per second square, and it is constant. It's not changing. I want to know at t equal 1 second, how much is omega and how much has the tire rotated, which is a very simple problem because it's a constant alpha, so I can easily go and grab these formulas, right? This constant alpha, I can come here. From these three formulas, I can grab any that I need. One of them is about omega. Since the time is provided, you see the omega shows itself in the first and third equation. But the third equation is time independent, so in order to know omega, you need to know the delta theta, which you don't. That's one of the unknowns of the problem. So I'm going to use the first formula because it has t, okay? So we say omega is equal to what? Omega naught plus alpha times t, and omega naught is 0, alpha is given, and t is given, so you're going to get 110 radian per second. Then you need to know delta theta. Delta theta, which is theta minus theta naught, you can see it here or here. So now it does not matter which one you are using. Why? Because if you use the second one, you have t in it, which you know. If you use the third one needs to know omega, but omega you just calculated. So now you can use either one. It does not matter. So I use second one and say delta theta is equal to omega naught times t plus 1/2 alpha times t squared, and I have all the parameters. This one is 0, this is 1, this is 110, this is 1. So you're going to get 55 radians, which if you divide by 2 pi, you can see how many revolutions has happened. Okay, so very, very simple problem once I know which formulas to use.